All right, now let's solve some trig equations where there's more than one type of trig function within that equation. So this is really the same process as we did before in the previous lesson, but we're really just going to be trying a couple of different types of equations here. All right, so let's look at this first one. So we've got 2 cosine x sine x minus cosine x. So if we think about this algebraically, this is not all that different from seeing something like this. We know that we would want to find a way to factor out any common factors. So in this case, our common factor is cosine x. So I'm going to say cosine x times 2 sine x is what's left over, minus 1 is equal to 0. Now that we've got two different factors, we can set each equal to 0. So x is equal to pi over 2 and 3 pi over 2. And I should probably say that these are my solutions from 0 to 2 pi. Let's keep track of these. 0 to 2 pi. Okay. And then 2 sine of x minus 1, well, that's going to give me sine x is equal to positive 1/2. And I can say from that, my solutions here are x is equal to pi over 6 and 5 pi over 6. And let's actually just sketch these out, again, just so that we can kind of visually see where these angles are. So we've got pi over 2, 3 pi over 2, and we also have pi over 6 and 5 pi over 6. So now that we have those, let's come up with the general solutions. Is there any way that we can express all the angles that have these terminal sides in the fewest number of equations possible? Well, I can see here that between pi over 2 and 3 pi over 2, these are going to be pi radians apart. So x is equal to pi over 2 plus pi n. And then with these angles here, I would be able to start then saying x is equal to pi over 6 plus 2 pi n, along with 5 pi over 6 plus 2 pi n. But wait, don't let the fact that I use these colors kind of mess with your mind here. Pause and ask yourself, is there actually a way that I can express all of my angles here with less than 2 equations, or less than 3 equations, I should say? And hopefully we see that, yes, there is. Hopefully we found that from pi over 6 to 5 pi over 6, this is 2 pi over 3 radians apart, as is this, as is this. So basically, all these angles here are 2 pi over 3 radians apart. So I can say actually pi over 6 plus 2 pi over 3n would be one of the equations. And then pi over 2 plus 2 pi n, basically any angle that lands in that position would be the other equation. Okay, so these would be all of our equations there. A little tricky, but I promise that as you work through more of these, you'll be able to see these a little bit more efficiently. All right, go ahead and try number 2 now. If you've had a chance to work through it, you'll see that we really can't do much. We can't use any identities. We can't combine any like terms. But what we can do is we can actually square both sides. And what this allows me to do is to express everything in terms of sine. Well, how so? Well, the left side, if I expand it all out, becomes this. The right side, cosine squared x, well, we know that cosine squared x is equivalent to 1 minus sine squared x. Now, if I can move all of my terms over to one side, I've got 2 sine squared x plus 2 sine x. 1 minus 1 is just equal to 0. And now I can factor out 2 sine x. And now I can set each of these equal to 0. So sine x is equal to 0. Here, sine x is equal to negative 1. So my angles from 0 to 2 pi, I would say x is equal to, this would give me 0 and pi. This would give me sine x is equal to 3 pi over 2. Okay? Now what about my general solutions? My general solutions, I would say x is equal to, if it helps to sketch these out, I've got 0, pi, and 3 pi over 2. So the best way to say this here, I would say 0 plus pi n and 3 pi over 2 plus 2 pi n. Now, I haven't boxed my answers Because I have not checked for extraneous solutions. And you might be thinking, what? Extraneous solutions? Why would I have to check for extraneous solutions here? Well, the fact that I squared both sides, what I'm essentially doing is I'm introducing a different set of trigonometric functions. In other words, I'm creating more solutions than might actually be there. So what I'm going to need to do is I'm going to quickly need to check for extraneous solutions. That is, take these angles here and check to ensure that when I plug them back into my original equation as you see it there, that both sides do indeed equal to each other. Unfortunately for us, these are pretty efficient and easy to check. Sine of 0 plus 1, is that equal to the cosine of 0? Well, 0 plus 1 is equal to 1, so this one does work. Well, try the next one. Sine of pi plus 1, is that equal to the cosine of pi? The sine of pi, well, that's going to be equal to 0, but the cosine of pi is equal to negative 1. So this one does not work. So pi turns out to be extraneous. And then finally, let's just do the check over here on the side. I can say sine of 3 pi over 2 plus 1, well, that's equal to 0. Cosine of 3 pi over 2, that would also be equal to 0. So this does work. So my angles that do work from 0 to 2 pi are 0 and 3 pi over 2. So these do work. Well, what about, how does that affect my general solutions? Now that I know I'm only looking at 0 and 3 pi over 2, I can just say 0 plus 2 pi n, or just 2 pi n, and then 3 pi over 2 plus 2 pi n. These would be my general solutions. Those are all the angles that satisfy this original equation. So when you're doing something like squaring both sides, you definitely want to make sure that you are checking for extraneous solutions because you are creating more variables than were originally there. Okay? All right, let's try another one. Let's try something like this. And there are a couple of ways that we could go about doing this, but I think something that's important to highlight here is that this is equivalent to the following. And you might be sitting there and thinking, can I just go ahead and multiply both sides by cosine of x? That is to say, can I do something like this? And the answer is yes, you can. However, you do want to consider here that we have a domain restriction, okay? Cosine x here cannot be equal to 0. So we cannot include any angles such that cosine of x would ever be equal to 0 because you can't ever divide by 0. And those angles are pi over 2 and 3 pi over 2. So what this is kind of a warning before we start that we cannot get pi over 2 and 3 pi over 2 as our actual solutions. And if you're having a hard time seeing that, maybe something that might be helpful is if I just took this and I rewrote it as the following. If I said, this is equivalent to 2 cosine squared x over cosine x plus 2 over cosine x, and make this 5 cosine x over cosine x. And what we could do here then is if I move all of these terms over to one side, now I'm able to write all of this over cosine of x, in which case I can actually factor cosine x out. That is to say, write it as 1 over cosine x. And these are equivalent. And now we can see here, we can really just solve this equation now, right? 2 cosine squared x minus 5 cosine x plus 2. And then just remember and ask ourselves, if I were to set this equal to 0, is there ever any x values such that this would ever be equal to 0? And the answer is no, right? There's no angle that could ever turn 1 over some function equal to 0. But I do also have that same set of domain restrictions. So we really just need to focus on this part right over here, which I will do in just a moment. But I do want to make sure that this is the same thing that we would get if we wanted to multiply both sides by cosine of x from the get-go. All right, so now that we understand that, let's go ahead and factor this. This is 2 cosine x, and if we're factoring here, this is 2, this is minus 1. Cosine x is equal to 1/2. Cosine x is equal to 2. This here is undefined. This here would give me angles, let's see, that's pi over 3 and 5 pi over 3. And then my general solutions, x is equal to pi over 3 plus 2 pi n, and 5 pi over 3 plus 2 pi n. Okay? All right. Let's do two more different types of equations here. Let's look at this next one here. You'll notice right off the bat, one of the unique things about this equation is that I actually have a coefficient in front of my x. So how does that change things? So we'll say sine of 2x, let's first off isolate this, is equal to root 3 over 2. So we're now asking ourselves, what is the angle such that I get root 3 over 2 when I take the sine of it? However, the angle, what I'm really asking is, what is the angle that when I multiply that by 2, I get root 3 over 2? And to help us kind of process this, I'm going to just temporarily call this angle in here theta. I'm going to say, all right, let's say sine of some angle theta is equal to root 3 over 2. Well, what would theta be? Theta could be pi over 3 and 2 pi over 3. So again, what have we done? We've let theta be equal to 2x. That's what we're doing here. All right, let me just switch that to a different color just so we can see. Okay, I'll switch that there. And what I'm going to proceed to do is I'm going to actually find the general solutions first. Okay, I'm going to say let theta be equal to, and if I sketch this out, I've got pi over 3 and 2 pi over 3. So my general solutions, I'd really have no other choice but to write this as pi over 3 plus 2 pi n. And the other one, theta is equal to 2 pi over 3 plus 2 pi n. So we've solved for theta, but we haven't actually finished solving for x. Now I'm going to replace theta with 2x. And 2x is equal to 2 pi over 3 plus 2 pi n. So now that I want to solve for x, I will say the following. X, if I want to isolate x, I'm going to divide everything by 2. So pi over 3 divided by 2 is pi over 6. 2 pi n divided by 2 is pi n. And then on this side, x is equal to 2 pi over 3 divided by 2 is just pi over 3 plus pi n. So now that I actually started and I found my general solutions first. These are my general solutions. But I'm now going to use those general solutions to come up with all my angles from 0 to 2 pi. What I'm effectively going to do is I'm going to start plugging in values for n until I've reached 2 pi. So that is to say, when n is equal to 0, I got pi over 6. When n is equal to 1, I've got 7 pi over 6. When n is equal to 2, wait a minute, pi over 6 plus 2 pi over 6 plus 2 pi. I already know that I'm getting an answer that's greater than 2 pi, so I don't want to include that. So I'm really going to stop there. Now let's move on to the other equation. When n is equal to 0 for the second equation, I get pi over 3. When n is equal to 1, I get 4 pi over 3. When n is equal to 2, all right, and that's, again, an angle that's going to be greater than 2 pi, so I would not include that. So I've now found my 4 angles such that when I plug them into my original equation, when I plug pi over 6 back into my original equation, does that work? Sine of 2 times pi over 6, does that equal root 3 over 2? Sine of pi over 3 is indeed root 3 over 2. And just kind of graphically, if we wanted to show these two angles here, what I just found was pi over 6. And when I multiply pi over 6 by 2, I end up at pi over 3. When I take 7 pi over 6, which is over here, 7 pi over 6, and I multiply that angle by 2, I'm back in that same spot, okay? Or I'm back, actually, not just there, I'm actually all the way around over here. And so I end up in that terminal position that I'm looking for. Well, what about something like pi over 3? Well, pi over 3 is right over here, so I'm definitely in the correct spot. But when I multiply pi over 3 by 2, I get 2 pi over 3, which places me over here, right? And when 2 pi over 3 is multiplied by 2, I get 4 pi over 3, which places me in the same spot as well, okay? So those are the angles effectively that I'm looking for to satisfy my equation, okay? Which would actually be down right over here. all right? Or let's just say 4 pi over 3, when I multiply that by 2, I'm going to get 8 pi over 3, which is right back, where are we? Right back over here. So I know graphically that might be a little hard to see, but hopefully that helps make sense as to what we're doing. We're taking our angles that when we multiply by 2, I'm in the terminal positions that I'm looking for, so that the sine of 2 times that angle is indeed equal to root 3 over 2. All right, let's do one more type of problem here. Go ahead and pause the video and see if you can first solve this algebraically. Well, if we go ahead and combine all the like terms, I've got the following. 4 tangent of x minus 3, tangent of x plus 2, tangent of x is equal to 3 over 4, and tangent of x then is equal to negative 2. Now, before you start thinking that these are undefined, ask yourself, tangent of what angle is equal to 3 over 4? And the answer that you might be thinking is, I don't know, because that's not a ratio that comes out of the values we're accustomed to working with in our unit circle. So as far as we know, we can just simply say x is equal to the arctangent of 3 over 4. Now, the issue with using arctangent, however, is that that's only going to give us one angle, but we know by now that there are two angles from 0 to 2 pi, such that tangent of x should be equal to 3 over 4. And perhaps sketching it might help out a lot. So let me actually just sketch arctangent of 3 over 4. So keep in mind, arctangent of 3 over 4 is some angle. I don't know where that angle is, but I know that if I'm taking arctangent of a positive input, this angle x is somewhere here in quadrant 1 because of what we know about the range of arctangent between negative pi over 2 and positive pi over 2. All right, so let me actually just label that. So I know that our angle x right now so far is in quadrant 1. Now ask yourself, where else would the tangent of my angle give us a positive output of 3 over 4? And it would have to be in quadrant 3. Tangent is positive in quadrant 3. Well, how can I express this angle here, this mystery angle here, in terms of x? Well, it's just pi radians away. So the second angle I could write is x is equal to arctangent of 3 over 4 plus pi radians. And again, do I know exactly what the value is? No. I know it's actually, if you want to put that in your calculator, x is approximately, I'll just say that, it's approximately 0.64 radians, but that's really beside the point. We just know that it's in quadrant 4 and quadrant 3. So we would express our solutions from 0 to 2 pi that way. Okay? So from 0 to 2 pi, we've got those angles. So there's one, and here's our other one. But that only took care of the first set of factors. Now let's look at these here. I'm going to switch colors here. So now, what about those? Well, we would say, where is tangent going to give us a ratio of negative 2? Well, if we say x is equal to the arctangent of negative 2, our angle x has to be in quadrant 2 somewhere. And actually, it's probably closer to a little bit something like this. So x is somewhere here. Now, if you look at this, though, what this means is that x currently is a negative angle. So if I want to express my angles from 0 to 2 pi, that means a positive angle from 0 to 2 pi, I would then have to come up with a positive angle such that I get a negative 2 when I take the tangent of it. Well, where is tangent negative? In quadrants 2 and quadrants 4. So the first thing I would do is I would say my angle has got to be the arctangent of negative 2 plus pi radians. That's going to place me right there. Okay, so that's going to give me this value, this angle here, which when I take the tangent of this angle, I'm going to get negative 2. Well, what about the other one? Well, I want to be in this spot down here in quadrant 4, but I want to have a positive angle. So how can I use x to write the positive angle? I would say x is equal to arctangent of negative 2, this time plus 2 pi. And these are my angles from 0 to 2 pi that satisfy that second factor. Okay? Now, what about the general solutions? Well, generally, we can just say for our first set of solutions here, x is equal to arctangent of 3 over 4, I should put parentheses around this, plus just pi n. And then for these two here, x is equal to arctangent of negative 2 plus pi n. All right. So some of the more unique cases, and I encourage you to keep working through the practice problems, and you'll be experts in this in no time.